Welcome to the Plain Books Podcast.
Today we are taking on quite a monumental task. We're going to try and guide you through the entire cosmos with a little help from one of the greatest minds of our time.
We are talking about Stephen Hawking and his incredible book, The Universe in a Nutshell.
That's right. And this book, it really has a clear mission. Hawking wrote it to share his sheer excitement, his passion for the discoveries being made in physics and cosmology.
Right, especially the things he had worked on since his first big book, A Brief History of Time. And he made a promise to the reader.
He did. The promise was to get these huge, sometimes, brain-breaking ideas across without drowning everyone in the heavy math that usually comes with them.
And he really pulls it off. I mean, the structure of the book is brilliant. It's almost like a tree.
Exactly. There's a central trunk of, let's say, required knowledge, and then you have these 7 branches that shoot off from it. Each one is a deep area of research he was involved in.
And the idea is once you get that central trunk, you can explore those branches in pretty much any order you want.
Which is what we're going to do. The goal for this episode is to give you a kind of comprehensive shortcut through all of it.
We want to distill these incredibly complex concepts. We're talking imaginary time, extra dimensions, all of it, into the essential nuggets of knowledge, the key insights.
So by the end of this, you will be, instantly well-informed on some of the biggest questions in science.
And our journey has to begin with the 2 great pillars of 20th century physics. That's general relativity and quantum theory.
And both of those are, completely tied to the work of one person who just fundamentally changed how we see everything: time, space, reality itself.
Of course, we're talking about Albert Einstein.
To really get this, you have to start with the man himself. Albert Einstein, born in Ulm, Germany, 1879. And what's so fascinating is how early his, let's call it his anti-authoritarian streak showed up.
He was a genius, obviously, but he hated the German school system. He actually left school in 1894 just because he couldn't stand how rigid and, military-like it was.
And that part of his personality, that questioning, argumentative nature, it never left him. It actually made things pretty difficult for him after university.
Right. Even after graduating from the ETH in Zurich, which is a world-class institution, no one in academia wanted to hire him. He was just seen as too difficult.
He was desperate for an academic job. He ended up, in 1902, taking a junior position at the Swiss Patent Office in Bern.
So his day job was looking at patent applications for, everyday inventions. And in his spare time, he was secretly rewriting the laws of the universe.
Which brings us to 1905, his Annus Mirabilis, the miracle year.
An unbelievable year. He writes 3 papers that launch not 1, but 2 complete conceptual revolutions in physics.
And the first of those revolutions, special relativity, it started by just demolishing this idea that had dominated science for centuries, the concept of the ether.
Explain the ether for us.
Well, before the 20th century, physicists just assumed that space couldn't be empty. It had to be filled with some kind of invisible substance, the ether, that light waves traveled through.
Kind of like how sound travels through air or waves travel through water.
Precisely. And this idea was so deeply embedded that people went to truly absurd lengths to try and measure it.
Hawking tells that great story about the Jefferson lab at Harvard.
Oh, it's a classic. They built this whole lab for super sensitive measurements, and to avoid any magnetic interference, they constructed it entirely without using any iron nails.
But the punchline is?
The punchline is they completely forgot that the bricks they used to build the walls were full of iron. So all that incredible effort was, let's say, slightly undermined.
A great little anecdote. But the real death blow to the ether came from an experiment, right?
It did. The Michelson-Morley experiment in 1887, they tried to measure the speed of light in different directions to detect the Earth's motion through this supposed ether.
And they found nothing.
Absolutely nothing. No difference. The result was a complete shock to the system. It meant the speed of light was constant no matter how you're moving. It's the universe's ultimate speed limit.
If you run towards a beam of light, it still moves away from you at the exact same speed. It's so counterintuitive.
It is. And before Einstein, other physicists like Fitzgerald and Lorentz tried to explain the experiment's result by saying that, maybe moving through the ether causes objects to shrink and clocks to slow down.
They saw it as a physical effect of this medium.
Right. But Einstein's genius was to say, No, there is no ether. This isn't some physical effect. This is a fundamental property of space and time themselves. They are relative.
And we've proven this. We see it every day in particle accelerators.
Every single day, particles are accelerated close to the speed of light, and we see their internal clocks slow down exactly as predicted. And then there's that famous experiment with the atomic clocks on airplanes.
They flew them around the world in opposite directions.
And when they landed, the clocks showed different times. The difference was tiny, but it perfectly matched the predictions of special relativity.
And Hawking has a great little jab in the book for anyone thinking they can use this for a long life.
He does. He points out that the tiny, tiny fraction of a second you might gain from time dilation is, quote, more than canceled by eating airline meals. A perfect dose of reality.
But special relativity created a new problem. A huge one.
A massive one. Newton's theory of gravity said that gravity's effects were instantaneous. If the sun vanished, the Earth would feel it instantly. But special relativity says nothing can travel faster than light.
So the two theories were in direct conflict.
A total conflict. And this is what pushed Einstein towards his next and even greater breakthrough, general relativity, in 1915.
The idea here is just beautiful. Gravity isn't a force pulling things together.
No. It's the result of mass and energy warping and curving the very fabric of four-dimensional space-time. As John Wheeler famously put it, space-time tells matter how to move, matter tells space-time how to curve.
It's a dance, a geometric dance.
It is. And it's worth noting, there was some drama around the discovery. The mathematician David Hilbert actually found the final equations just a few days before Einstein did.
But Hilbert himself gave all the credit for the core physical idea to Einstein.
He did. He recognized that the concept of gravity as geometry was Einstein's alone.
And the confirmation of this theory was a global event.
Huge. A 1919 British expedition went to West Africa during a solar eclipse. They measured the light from a distant star passing near the sun.
And they saw it bend.
It bent. Exactly as Einstein's theory of curved spacetime predicted it would. It made him an overnight global superstar.
But this is where even a mind like Einstein's can be limited by its own assumptions.
Yes, because the equations of general relativity were very clear about something. The universe could not be static. It had to be either expanding or contracting.
But Einstein and pretty much everyone else at the time just believed in a static, eternal universe. It was the common sense view.
So he fudged his own equations. He added a new term, the cosmological constant, which was basically a repulsive force designed to perfectly balance gravity and keep the universe frozen in place.
Hawking calls this one of the great missed opportunities in the history of physics.
It really was. If he had just trusted his math, he would have predicted the expanding universe a decade before anyone observed it.
Instead, it took Edwin Hubble in the 1920s, using the giant telescope on Mount Wilson, to prove it. He saw that all the other galaxies were flying away from us.
And the farther away they were, the faster they were receding. The universe was undeniably expanding.
And if you run that movie backwards,
You inevitably end up at a single point, a beginning. What Georges Lemaitre called the primeval atom, we call it the Big Bang.
a point about 13.8 billion years ago, when everything in the universe was compressed into a state of infinite density, a singularity.
And this is precisely where general relativity fails. It predicts that time itself began at the Big Bang singularity and that it ends inside black holes. But the math, the equations themselves, just break down at the singularity. They give you nonsense answers, like dividing by zero.
It's a signpost.
It's a giant flashing neon sign saying, this theory is incomplete. To go any further, we have to bring in the other great pillar of modern physics.
We have to go from the infinitely large to the infinitely small. We have to talk about quantum theory.
Right. And that revolution started very quietly, back in 1900, with Max Planck. He suggested that light isn't a continuous wave, but comes in tiny, discrete packets. He called them quanta.
And Einstein himself was a quantum pioneer. His Nobel Prize wasn't even for relativity.
No, it was for his 1905 paper explaining the photoelectric effect using these quanta of light. That idea is the bedrock of, everything. Solar panels, digital cameras, modern electronics.
But the part of quantum theory that really shattered everything, and the part Einstein fought against for the rest of his life, was the uncertainty principle. Werner Heisenberg's big idea. It says you can never, ever know both the exact position and the exact speed of a particle at the same time. The more you pin down one, the fuzzier the other one becomes.
Which means the universe, at its most fundamental level, is not deterministic. It's probabilistic.
It's based on chance. And this randomness just horrified Einstein. It led to his famous quote, God does not play dice. He couldn't accept it.
But the rest of science did. They had to. Quantum mechanics just worked. It explained atoms, chemistry, everything. It's the foundation of all our modern technology, even if it destroyed that old dream of a perfectly predictable clockwork universe.
So what's the final epitaph for Einstein in this chapter?
I think it's his own words. He said, "Politics is for the moment, but an equation is for eternity." And his equations for general relativity, which described the grand shape of the cosmos, they are his memorial.
So we left general relativity at a crisis point, the singularity. Einstein's math just gives up at the Big Bang.
Yeah.
To get past this, Hawking says we need to adopt a different way of thinking, a philosophical stance.
Yes, this is a really crucial point. He champions an approach called positivism.
Which sounds complicated, but the idea is actually very pragmatic.
It is. Positivism basically says that a scientific theory is just a mathematical model, and its only job is to describe what we observe and make predictions we can test. That's it.
So we shouldn't ask questions like, what is time, really?
Exactly. You can't ask what it is. You can only ask what your model, your theory, predicts that your clock will measure. This move is so important because it gives physicists permission to use some very strange mathematical tools.
Like imaginary time, which we'll get to.
Right. So in general relativity, time is just something you measure inside the universe. It's not some absolute clock ticking away in the background.
Which means time itself can have a beginning and an end.
And if time is defined by the universe, then asking what happened before the Big Bang is a meaningless question. It's like asking what's north of the North Pole. There's no before if time itself begins there.
And Hawking, along with Roger Penrose, actually proved that a beginning was unavoidable.
They did. They showed that because our universe is full of matter and energy, which bends light inward, you can trace it all back and prove it must have started from a singularity.
And Hawking throws in a little story here about the Cold War physics scene.
Oh, it's great. These two top Soviet scientists, Lifshitz and Klatnikov, they had published papers claiming that singularities could be avoided. This fit with the Soviet ideology of an eternal cyclical universe.
But they were wrong.
They were wrong, and they had to backtrack. But they did it very cleverly. They found a more general proof that singularities were inevitable, and then they claimed that discovery for the Soviets. A bit of political face-saving.
So back to the quantum world. The uncertainty principle gave us randomness. But when you apply it to energy, you get an even bigger paradox.
You do. Because of uncertainty, nothing can ever be perfectly still. Even in its lowest energy state, what we call the ground state, there have to be these tiny jiggles, these zero-point fluctuations.
And this applies to empty space too, the vacuum.
Yes. The vacuum is not empty, it's fizzing with these energy fluctuations, waves of all possible wavelengths. And here's the problem. Every single one of those possible waves has a little bit of ground state energy.
And since the wavelengths can be infinitely short,
if you add up all that energy in any given region of space, you get infinity. An infinite energy density everywhere in the vacuum.
and according to general relativity, energy creates gravity.
So this infinite energy should have created an infinitely strong gravitational pull that would have instantly crushed the entire universe down into a single point.
Which clearly has not happened.
No. So we have a major contradiction. Our two best theories are giving us a result that is violently wrong.
And we can't just ignore this vacuum energy because we know it's real.
We know it's real because of something called the Casimir effect. If you put two metal plates very, very close together in a vacuum, something strange happens.
The space between the plates restricts which wavelengths of these vacuum fluctuations can fit.
Right. There are fewer possible waves between the plates and outside them. And this difference in energy density creates a tiny but measurable force that pushes the plates together. That force is real. So that energy is real. We have to deal with the infinity.
And the solution that physicists came up with is, well, it's called supersymmetry.
It's a beautiful, elegant idea from the 1970s. You can't just wish the infinities away. You need a physical reason for them to cancel out.
And it all comes down to a property of particles called spin.
Exactly. Supersymmetry proposes that every known particle has a secret superpartner with a slightly different spin. Now, particles called bosons, the force carriers, they contribute positive energy to the vacuum.
And particles called fermions, the matter particles like electrons, they contribute negative energy.
And the magic of supersymmetry is that in a perfectly supersymmetric universe, the positive infinities from all the bosons would be perfectly canceled out by the negative infinities from all the fermions. The total is zero. Problem solved.
For a while, this led to a theory called supergravity. But then in the 80s, the focus shifted.
It shifted in a big way towards supersymmetric string theory, the idea that the fundamental building blocks were tiny, vibrating strings.
Hawking says it felt a bit like a change in fashion.
It did. The argument was that while supergravity canceled the biggest infinities, string theory could cancel out even the smaller leftover ones. But the math was just horrendous.
He jokes that it would take a good student 200 years to check the calculations.
Right. But then something amazing happened, a discovery called duality.
Which means,
It means different math, same physics. It turned out that the 5 different string theories people were working on and supergravity were all just different mathematical descriptions of the same underlying reality.
they were looking at the same elephant from different angles.
A perfect analogy. It was a huge lesson for theoretical physics.
Which brings us back to the Big Bang and the ultimate mathematical tool for fixing it, imaginary time.
Okay, this is where it gets weird, but just remember the positivist approach. It's a mathematical tool.
It's time measured in imaginary numbers, which are numbers that involve the square root of -1. For the listener, this sounds like pure fantasy.
It does. You can't get an imaginary gas bill, but as a mathematical model, it's incredibly powerful, and it's the key to the Hartle-Hawking no-boundary proposal.
Their idea for how the universe began.
Right. If you describe the history of the universe using imaginary time instead of real time, something amazing happens. The Big Bang's singularity, that sharp, problematic point,
It gets smoothed out.
it becomes the South Pole on a smooth, four-dimensional sphere, a perfectly normal, regular point where the laws of physics work just fine. There's no breakdown. The beginning of the universe becomes just another point in space-time.
So there's no edge, no boundary, just a smooth, closed surface.
And this imaginary time trick also works for black holes. At the event horizon of a black hole, imaginary time basically stands still, just like lines of longitude all meet and stop at the poles. And this mathematical fact implies that the black hole must have a temperature.
And entropy,
Yeah.
which is a measure of information.
A measure of its internal states, yes. And that leads to this incredibly deep idea called the holographic principle, the idea that all the information contained within a volume of space.
Can be fully encoded on its two-dimensional boundary, like a hologram.
Exactly. And that idea will be absolutely critical when we try to figure out what happens to things that fall into a black hole.
Okay, let's zoom out. We're now looking at the universe on the largest scales. Billions of galaxies scattered more or less evenly. And this view presents a really old puzzle, Olber's paradox.
It's a simple but profound observation. If the universe was infinite in size and had existed forever, then no matter where you looked in the night sky, your line of sight would eventually land on a star.
So the entire night sky should be as bright as the surface of the sun.
Right. The fact that it's dark tells you something fundamental. The universe can't have existed forever in its current state. Something must have happened.
And that something was the Big Bang, confirmed by the observation that the universe is expanding.
Confirmed by Sliver and Hubble in the 1920s. Every galaxy is flying away from every other galaxy.
And tracing that back in time brings us, again, to the singularity where general relativity breaks down. Hawking is really firm on this point. Science can't just give up at the origin.
He says a law of physics isn't really a law if it only works sometimes. It has to apply everywhere, including the very beginning.
And to do that, you have to fully embrace the quantum nature of that beginning. When the universe was tiny, the uncertainty principle wasn't just a small effect, it was the law.
Right. Einstein may have hated it, but as Hawking says, all the evidence suggests God is quite a gambler.
You can think of it like this. When the universe is big, like today, there are so many quantum dice rolls that they all average out to predictable classical behavior.
But when the universe was microscopically small, there were only a few dice rolls, and pure randomness ruled everything.
And this means you can't talk about the history of the universe.
No. You have to use Richard Feynman's idea of a sum over histories. The universe doesn't have a single definite past. It has every possible past, every possible history, all at once.
Including histories where, as Hawking jokes, Belize wins every gold medal at the Olympics.
Right. It's just that those histories have an incredibly low probability.
So how do you make sense of this infinite number of possible histories?
You go back to the no-boundary condition. The most natural, simple assumption is that the universe, in imaginary time, is a finite, closed surface with no edge, a smooth sphere.
And that simple, smooth sphere in imaginary time corresponds to a very specific kind of history in real time.
It corresponds to a universe that undergoes a period of incredibly rapid exponential expansion right at the beginning, a process called cosmic inflation.
And inflation is so important because it explains why the universe is so smooth and uniform on large scales today. It basically stretched out all the initial wrinkles.
It also solves the energy problem. Inflation gives us a way for the universe to have a total energy of zero.
How does that work?
It essentially borrows energy from the gravitational field to create all the matter we see. The positive energy of matter is perfectly balanced by the negative energy of gravity.
Hawking's line is great here. If only banking were so simple.
Exactly. A universe from nothing isn't a problem if the books are perfectly balanced at zero.
But our universe isn't perfectly smooth. We have galaxies, stars, us. We have structure.
True. And that's because the most probable histories under the no-boundary model aren't perfectly smooth spheres. They're slightly lumpy, slightly deformed spheres.
Hairy spheres, as he calls them.
Right. And those tiny initial lumps in imaginary time correspond to universes in real time that inflate, but then the expansion slows down just enough for gravity to take over and pull matter together into clumps.
And we've seen the evidence for these initial clumps. The Kobe satellite.
Yes, the Cosmic Background Explorer. It mapped the faint afterglow of the Big Bang, the microwave background radiation, and it found these tiny temperature fluctuations, tiny variations, just 1 part in 100,000.
And that map, those little hot and cold spots.
That map is the blueprint. It's the seed from which all the structures in the universe, galaxies, stars, planets grew.
Which leads us to a very controversial but powerful idea. The anthropic principle.
It's the simple observation that the universe must have the properties that it does, because if it were different, we wouldn't be here to observe it.
We can only exist in one of that tiny, tiny fraction of possible histories that allows for things like stars and galaxies to form.
It's a kind of selection effect, and you can use it to explain some very basic things, like why we live in 3 spatial dimensions.
Right. In a two-dimensional universe, a complex animal couldn't have a digestive tract without falling into 2 pieces.
And in a universe with 4 or more large spatial dimensions, gravity would be much stronger over short distances, and planetary orbits would be unstable. Planets would either fall into their star or fly off into space.
So only 3-dimensional universes can support stable life over billions of years.
It seems so. And the anthropic principle also helps us with that cosmological constant, Einstein's biggest mistake.
The energy of the vacuum.
Yes. Quantum theory says it should be there, and observations now suggest there is a small amount of it, and it's causing the expansion of the universe to accelerate.
But it has to be incredibly small.
Incredibly, ridiculously small. If the vacuum energy were much larger, its repulsive force would have been so strong that it would have torn everything apart before gravity ever had a chance to form galaxies. No galaxies, no stars, no us.
We live in a universe where the dice just happen to roll in our favor.
We are the survivors of a cosmic lottery.
Okay, so the ultimate goal of physics, for centuries, was prediction. This was Laplace's dream.
The idea of scientific determinism. He imagined that if you could know the precise position and speed of every single particle in the universe at one moment,
You could calculate the entire future and reconstruct the entire past. A perfect clockwork universe.
that dream is dead for a couple of reasons. The first is practical. Chaos theory. The butterfly effect.
Tiny, tiny differences in the starting conditions lead to massively different outcomes down the line. Is why we can't predict the weather more than a week or so out.
Exactly. But the real killer for determinism is quantum mechanics. The uncertainty principle makes it fundamentally impossible to even get that perfect starting data that Laplace needed.
You can't know both the position and the speed perfectly.
So as Hawking says, if we put lousy data in, we will get lousy predictions out.
So what replaced Laplace's dream? What's the new quantum version of determinism?
Well, the best you can do now is predict how the wave function will evolve over time. The wave function is basically a cloud of probabilities for where a particle might be and how fast it might be going.
And we have an equation for that, the Schrödinger equation.
We do. And it's deterministic in its own way. It tells you exactly how that probability cloud will change. But you can't save classical determinism by just saying, oh, the particle really does have a definite position. We just can't see it.
Those are hidden variable theories.
And they've been ruled out by experiments. The universe is fundamentally fuzzy. Even a hypothetical God would only know the wave function, not the definite answer.
But all of this assumes that space-time is smooth and predictable. And general relativity tells us that's not always the case.
It allows for black holes, places where space-time is so warped that time itself breaks down. It's an old idea, actually. John Michell proposed dark stars way back in 1783.
Stars so massive that light couldn't escape.
Right. But the modern concept comes from general relativity. It's a region where the escape velocity is greater than the speed of light.
Einstein himself didn't believe they were real.
He didn't. But the evidence started piling up, especially in the 1960s, with the discovery of quasars, which seem to be powered by matter falling into something incredibly dense and massive.
So how does a black hole form?
You need a really big star, more than twice the mass of our sun. When it runs out of nuclear fuel, its own gravity causes it to collapse catastrophically, crushing all its matter down into a singularity of infinite density.
And the boundary around that is the event horizon, the point of no return.
It's formed by the paths of light rays that are trying to escape but are just trapped, hovering on the edge.
And it's important to stress, if our sun were to magically turn into a black hole right now, Earth's orbit wouldn't change at all.
Not one bit. The mass is the same, so the gravity at our distance is the same. It's not a cosmic vacuum cleaner.
But black holes present a huge crisis for quantum determinism, the information paradox.
This is the core problem. Let's say an astronaut falls into a black hole. According to quantum mechanics, we should be able to reverse the Schrödinger equation and figure out everything about the astronaut's past.
But we can't.
We can't, because the astronaut's wave function, all the information about them, is now inside the event horizon, completely cut off from our universe. It's gone. We've lost a piece of the puzzle.
And if you lose information, you lose predictability. You lose determinism.
Which led Stephen Hawking to his most famous discovery, Hawking radiation.
It all goes back to those vacuum fluctuations we talked about.
Exactly. The vacuum is full of pairs of virtual particles that pop into existence and then immediately annihilate each other.
But near the event horizon of a black hole, something different can happen.
Yeah. The intense gravity can pull a pair apart. One particle might fall into the black hole, but its partner can escape out into space.
And the particle that falls in has negative energy?
It has to balance the books. This means the black hole actually loses a tiny bit of mass. The particle that escapes carries away positive energy, and we see it as thermal radiation. The black hole glows.
So black holes aren't actually black, and they're not eternal. They evaporate.
They shrink over vast timescales, radiating away their mass until eventually they disappear completely in a final puff of radiation.
And this creates the ultimate paradox. If the black hole disappears, what happens to the information about everything that fell into it? The astronaut, the star, everything.
If that information is truly gone forever, then determinism is dead. Utterly. We can never be certain about the past because anything could have been thrown into a black hole that has since evaporated.
This was and is a huge debate in physics, which led to a competing idea.
A way out from the world of string theory. The P-brain model.
In this picture, a black hole isn't a point. It's more like a complex intersection of surfaces or brains.
And the idea is that the information isn't lost. It gets encoded in vibrations, in waves on the surface of these brains. So as the black hole evaporates, that information is slowly, and probably in a very scrambled form, released back into the universe.
So physics is at a crossroads. Is information lost and determinism is just an approximation? Or is information conserved, as the P-brain model suggests?
It's one of the biggest open questions. And Hawking ends the chapter with a nod to his famous appearance on Star Trek, playing poker with Newton and Einstein.
A perfect image, suggesting that if information really is scrambled and returned, something completely unexpected might pop out of the chaos.
Which leads us naturally from black holes to another staple of science fiction, time travel.
This was a topic that serious physicists avoided for a long time. It was seen as, well, not serious.
It was taboo. Hawking gives a lot of credit to his colleague, Kip Thorne, for being brave enough to tackle it scientifically.
He points out that scientists often use code words for it, like closed time-like curves, just to avoid getting ridiculed or having their research classified by the military.
Because the fear is always the same. Paradox. The grandfather paradox. What happens if you go back in time and kill your own grandfather before he meets your grandmother?
You'd never be born to go back in the first place. It breaks causality.
The main theoretical vehicle for this is the wormhole, a hypothetical tunnel through space-time that could connect two very distant points, or even two different points in time.
The shortcut.
The cosmic shortcut. In theory, you could use one to cross the galaxy and, as Hawking says, be back in time for dinner.
And if you can do that, you can manipulate the two ends of the wormhole to create a time difference between them. You can enter one end and come out the other end before you went in.
So we have to ask, do the laws of physics allow this? At the classical level, with just general relativity, it seemed unlikely at first. But then Kurt Gödel found a solution to Einstein's equations for a rotating universe that did contain these time loops.
It shocked Einstein.
It did. But to build a time machine you can actually use, something finite, you need a special ingredient. You need matter with negative energy density.
Stuff that pushes space-time apart instead of pulling it together. Anti-gravity, essentially.
In a sense. And classical physics forbids this. It says energy is always positive.
But quantum mechanics, as usual, changes the game.
It does. We've already seen with the Casimir effect and Hawking radiation that quantum fluctuations can create localized pockets of negative energy. So in principle, you might be able to gather enough of this exotic stuff to prop open a wormhole.
This is what forced Hawking to come up with a defense mechanism, the chronology protection conjecture.
His idea that the laws of physics must have some built-in feature that prevents macroscopic time travel, that protects the past from being changed.
And what's the fatal flaw in the time machine design?
It's the horizon, the boundary where the time loops begin. At this boundary, you'd have paths for light and for virtual particles that loop around and come back to where they started.
They travel on a closed loop in space-time.
Right. And a virtual particle traveling on one of these loops would bring its energy back to the same spot over and over and over again. When you add all that up, the energy density right on the time machine's horizon becomes infinite.
A wall of infinite energy.
Exactly. Any person or ship trying to cross that boundary to enter the time-traveling region would be, as Hawking puts it, wiped out by a bolt of radiation.
It's a self-destruct mechanism built into the laws of physics.
It seems so. The math, using that sum over history's idea, shows that the probability of space-time warping itself enough to create a time machine gets closer and closer to zero as you approach the threshold.
He even gives a number for the probability of Kip Thorne pulling off the grandfather paradox.
It's one of the most absurdly small numbers you can imagine. Less than one chance in 10 to the power of 10 to the power of 10 and so on. 6 times. It's basically zero.
And he ends with that great joke about the picture of Kip Thorne in the book.
That it's a little fuzzy just in case some bastard from the future came back and killed his grandfather. It's his way of saying that while it's almost certainly impossible, the universe always keeps a tiny sliver of uncertainty.
So, having protected the past, we now turn to the future, our future. And Hawking starts by challenging the typical sci-fi vision.
The Star Trek vision. This idea of a future where humanity has sort of arrived. We solved all our problems, our technology is stable, and things are pretty static. Hawking says this is completely unrealistic.
He argues there's no evidence in our entire history to suggest that growth or change will ever stop. If you look at the big picture, since the last ice age, complexity has only ever gone up.
And that growth is exponential. Population doubles every 40 years or so. Electricity use, the number of scientific papers published, they're all on these steep upward curves.
And those curves can't continue forever. They run into hard physical limits.
He does the math. If the current trends continue, by the year 2600, the human population would be standing shoulder to shoulder on all the land on Earth. And our power consumption would make the planet's surface glow red hot from waste heat.
Clearly, that's not going to happen. Something has to change.
Something has to give. And for Hawking, the answer isn't that we'll destroy ourselves. The answer is that we will have to evolve beyond our current biological limitations.
He draws a distinction between two kinds of evolution.
Biological evolution, which is our internal record, our DNA, that changes incredibly slowly through random mutations. Maybe one bit of useful information gets added per year on average.
But then there's our external evolution. Our knowledge.
Everything we store in books, on computers, on the internet, that is evolving at a blistering pace, millions of bits per second. And that is the reason, the only reason, humans dominate this planet.
But he predicts we are on the verge of taking control of our internal evolution too, the post-human future.
He was convinced that within the next 1,000 years, we would have the technology to completely redesign our own DNA, to improve ourselves.
Which is going to create enormous social and political problems. The improved versus the unimproved.
Huge problems. But he thought it was probably inevitable. The pressures to adapt, to improve ourselves for challenges like long-distance space travel will just be too great.
He even suggests we'll overcome one of our biggest physical limitations, the size of the birth canal, which limits the size of our brains.
He thought that within a century, we could be growing babies outside the human body, removing that constraint entirely.
And all of this is happening while we are in a race with another kind of intelligence.
Electronic intelligence. artificial intelligence. At the time he was writing, he pointed out that our best computers were still less complex than the brain of an earthworm.
But Moore's law, the doubling of computer power every 18 months, is changing that picture very, very quickly.
It can't go on forever, but it will almost certainly continue until computer complexity reaches and then surpasses the human brain.
And his logic is simple. If complex arrangements of chemical molecules can be intelligent, there's no reason that equally complex arrangements of electronic circuits can't be intelligent too.
And once an AI reaches human-level intelligence, it will be able to design even better, more intelligent systems than itself. You get a runaway intelligence explosion.
The ultimate future, then, is not the safe, comfortable world of Star Trek.
Not at all. It will be dynamic, dangerous, and rapidly changing. The beings that exist a few centuries from now, whether they are biologically enhanced humans or purely electronic intelligences, will be as different from us as we are from that earthworm.
Our final journey takes us to the smallest possible scales of reality. We know atoms are made of protons and neutrons, which are made of quarks. But does it stop there? Is there a smallest doll in the Russian nesting doll?
There seems to be a fundamental limit, the Planck length. It's the smallest distance you can possibly probe because if you use any more energy to look closer, that energy would collapse into a tiny black hole and hide what you were trying to see.
And it's an impossibly small scale, a millimeter divided by 10, with 34 zeros after it.
Right. To build a particle accelerator powerful enough to see that small would require a machine bigger than our entire solar system. So we need a theory.
We need M-theory, the only current candidate for a theory of everything.
It's the framework that attempts to unite all the different string theories and supergravity into one coherent picture, but it comes with a strange requirement.
It needs more dimensions, 10 or 11 of them.
For a long time, the standard explanation was that those extra dimensions are there, but they're curled up into a tiny, tiny ball at every point in space, so small we could never notice them.
But then a new radical idea came along, the brain world scenario.
This is one of the most exciting ideas in modern physics. It suggests that maybe one or more of those extra dimensions aren't small at all. Maybe they're large or even infinite.
And the reason this is so exciting is that it might be testable.
Exactly. We might be able to see evidence of these large extra dimensions at the Large Hadron Collider, the LHC, or in new high-precision gravity experiments.
So what's the model? How does it work?
The idea is that our entire universe, all the particles and forces we know, except for gravity, is confined to a three-dimensional surface, a three-brane, that is floating in a higher dimensional space called the bulk.
We're living on a sheet of paper in a larger room.
A perfect analogy. And this model offers a stunningly elegant explanation for one of the biggest mysteries in physics. Why is gravity so incredibly weak compared to all the other forces?
Weaker by a factor of trillions and trillions.
Because, the theory says, forces like electromagnetism are trapped on our brain. Their influence is concentrated here, so they're strong. But gravity isn't trapped. It can leak out into the bulk, into those extra dimensions.
So its strength gets diluted, it spreads out.
And by the time we feel its effects on our brain, it seems incredibly weak, which is why you can overcome the entire gravitational pull of the Earth with a tiny refrigerator magnet.
And if this is true, we should be able to measure it.
We should, at very, very small distances smaller than the size of the extra dimensions. Gravity shouldn't have had a chance to leak out yet, so it should be much stronger than what Newton's law predicts. Experiments are underway right now, trying to find that deviation.
And this idea could even explain dark matter.
It could. Imagine there's another brain, a shadow brain, floating parallel to ours in the bulk, very nearby.
We would never be able to see it because its light would be trapped on its own brain.
But we would feel its gravity. Gravity passes through the bulk. The gravitational pull from the matter on that shadow brain would look to us like invisible dark matter, exactly what astronomers need to explain why galaxies spin the way they do.
It all comes together. So the history of our brain, our universe, in imaginary time,
would be a four-dimensional sphere. The universe in a nutshell, the boundary of a five-dimensional bubble floating in the bulk.
and the anthropic principle still applies. Only the slightly lumpy, irregular nutshells will slow their expansion enough to form galaxies and allow for observers like us to exist.
It's a complete picture. And the LHC in Geneva might be the place where we find the first proof, if it ever detects a particle that seems to vanish, having briefly leaked off our brain into the bulk.
Which brings us to Hawking's beautiful final line, twisting Shakespeare's The Tempest.
Oh, Brain New World. That has such creatures in it. That is the universe in a nutshell.
What an absolutely immense journey from the geometry of space-time with Einstein through the total chaos of the quantum world and into the very architecture of time itself.
Yeah, we've navigated revolutions in thought. We've grappled with the paradox of information inside a black hole, and we've seen how the universe itself seems to protect the past from being changed.
If there's one single theme that runs through this entire book, one essential insight to take away, what would you say it is?
I think it's that certainty is an illusion. The old classical dream of a predictable, deterministic universe is dead. It's been replaced by a universe that is fundamentally governed by probability, by chance, by complex histories and imaginary time.
The universe isn't a finished, stable thing. It's uncertain at its very core.
Exactly. And the ultimate purpose of gaining this knowledge is to apply it. The ideas Hawking presents, they challenge your most basic assumptions about reality, about destiny, about what's even possible.
So our challenge to you, the listener, is to really engage with that, to participate in this knowledge by recognizing the uncertainty and complexity in your own life, and to see it not as something to fear, but as a source of vast potential.
Absolutely. The universe isn't a static product that's just waiting for us to figure it out. The real takeaway here is to see the exponential potential for growth, for change, in both our biology and our technology.
We are not heading for a safe, comfortable Star Trek future.
Not at all. We are heading into a future that is, both terrifying and thrilling, a future that's evolving at an incredible rate and demands that we embrace that change. Let the ideas in this book enhance your life by embracing that exhilarating reality.
And if you found this conversation captivating and you want to see the astonishing diagrams and go even deeper into the analysis that makes these ideas come alive, we really strongly urge you to purchase the book, The Universe in a Nutshell by Stephen Hawking.
And please engage with these concepts and with the community. Join the conversation on social media. Share your own thoughts on what these discoveries mean.
Thank you so much for joining this episode. We invite you to follow, subscribe, and share the Plain Books podcast with anyone else who seeks knowledge and insight into the great questions of science and the cosmos.
So we'll leave you with one final thought to explore on your own. We've talked about the brain world idea, that we live on a three brain and gravity seems weak because it leaks into the higher dimensional bulk. But what if that principle applies more broadly? What if a force we perceive as incredibly strong and local, like the strong nuclear force that holds atoms together, is actually just a weak force from another brain, but it seems strong to us only because its force-carrying particles are trapped here? Does that mean every particle in your body is just a ripple on a hidden cosmic ocean? And that reality is defined not by what it is, but by its boundaries.